Welcome and hello. This is a video lesson in the FHWA hydraulic toolbox, specifically about the rational method calculator. So if you're following along, this is the interface right here, the graphical user interface for the hydraulic toolbox. And if you want to add a rational method analysis, just go up to the calculators and then click on New Rational Method Analysis right here. You can also add a rational method analysis, i.e. the calculator, by clicking on the button on this toolbar, which is this button right here. The title bar says New Rational Analysis if you hover over, and then boom. The last way to add the rational analysis, the rational method calculator, is to right click on your project and then New Rational Method Analysis. Okay, let me go ahead and delete those one more time. Okay. Also, if you don't see this calculator's toolbar right here, you can go ahead and add that by going up to the display menu, toolbars, and then for some reason it's tools, not calculator. It'd be helpful if this was labeled calculator, but that's how to toggle it off and how to also toggle it back on. Click on tools and then boom, here is that toolbar, which I'm going to dock up here at the top of my user interface. All right, so let's use this rational method analysis calculator tool and double click to open, or we can go right click, rational method data. This is the interface that we're going to be talking about in this lesson. All right, let's just first check out the user's manual here for the rational method calculator. This is the PDF user's manual, starting on page 32 here, chapter 9. The icon for the rational method calculator is this little watershed icon right here. So this is the image that you'll be seeing on the button when you click on, this button right here, when you add a new rational method calculator to your project. Here's the interface. Here is the rational method calculation. By the way, if you haven't already downloaded this PDF file, the user's manual, you can do that by going up to the help menu and then this first link here for hydraulic toolbox user's manual, that will open up a PDF. So where were we? Here is the equation now for the peak discharge calculation. The rational method is a simple, widely used hydrologic formula for estimating the peak discharge from a small drainage area during rainfall events. This is a little bit more information than the user's manual provides. It's based on the idea that the maximum runoff rate occurs when the entire watershed is contributing to the flow at the outlet. That is, after a time equal to the watershed's time of concentration. So here are our parameters. Q is the peak discharge. That's what we're calculating in units of cubic feet per second. CIA is the product of three different terms that we multiply together. C is the rational method runoff coefficient. This is a fraction of the rainfall that becomes a runoff based on the land use, the slope, and the soil type. So that number is going to range from 0 to 1, but most likely between maybe 0.2 and 0.8. We'll get some examples of that a little bit later. I is the intensity of the rainfall in inches per hour for a duration equal to the time of concentration and for a chosen storm recurrence interval. And then A is the area of the watershed or the subbasin in acres. And then when you multiply all this out, you'd also have to multiply by a conversion factor of 1.00833 so that your acre inch per hour gets converted to CFS. There are some built-in assumptions for this equation, which also are not mentioned here in the user's manual. For instance, it's best used for smaller watersheds, and it only predicts peak discharge, not a full hydrograph. And finally, it assumes that the rainfall is uniformly distributed over the area and that the storm duration is at least as long as the time of concentration. All right, so let's go back to our hydraulic toolbox. What you may want to do is rename this calculator. So for instance, if this was for a specific watershed, you may call it subbasin, how about 28 100-year event. I'm just making something up here so it's a little bit more descriptive. So you can have a number of different calculations with distinct labels. So once you go ahead and define the data, you know that's associated with a specific subbasin or watershed and a return period. All right, so let's talk about the interface finally. What we're going to calculate is this peak discharge, which is a flow rate, Q, and then here are our terms, C, I, and A. The C value here is the runoff coefficient. C, typically the lowest of numbers would be closer to 0.1 for things like parks and open spaces where you wouldn't have much runoff based on the land use and the soil type. And then some of the higher numbers could be as high as, say, 0.95 for very dense commercial urbanized environments for large runoff percentages. We're just going to go ahead and make up a number, say 0.55, which is somewhere between the two. For the area here, this is in units of acres. So I'm just going to make something up. I'm just going to say, how about 40 acres? All right. And then the rainfall intensity, if I know what the rainfall intensity is based on the storm duration as well as the storm recurrence, I could just make something up for the sake of getting a calculation in here quick. I'll say 2 inches per hour. And then when I tab off that field, boom, here is my flow rate. The peak flow rate is 44.4 CFS. So you can go ahead and do the math yourself, multiply 0.55 times 40 times 2 times that conversion of 1.00833, it should come out to 44.4. Not much is said in the user's manual about the runoff coefficient or the area. The area itself should be pretty constant. The runoff coefficient, I can understand how that may change or that could be subject to interpretation, but the user's manual goes into the most detail about this rainfall intensity, which is in units of inches per hour. So if you wanted to open up the calculator to get more detail on how this number is calculated, go ahead and click on the compute button and then opens up this dialog box right here. Put it here. And you see at the top, we have a few different frames. First, there's the IDF curve computation. Below that, the time of concentration. And then finally, the intensity computation. So right now it's set at 2 inches per hour because that's what we had it at earlier when I just typed it in. But what we're going to be using this interface for is to get a new intensity, which is based on much more detailed information. And that's what I'm going to describe now. All right, so let's start at the top. Here we have the IDF curve computation. We have a few different options. First is Hydro 35 data used in the eastern United States. And there's NOAA Atlas 2 data used in the western United States. If you're outside the United States, not a problem. You can just manually enter that data here as well for user supplied data. So let's just check out these three options. The first is Hydro 35 data. If I click on that, then click on Define Storm Data, it opens up this dialog box where it's asking me to type in the depth of precipitation for these 6 different data points. There's the 2-year and 100-year for the 5, 15, and 60-minute storm durations. If you don't know what that is, then there is a reference. I'm going to leave a link in the description of this video, and it's going to bring you to this NOAA Technical Memorandum, NWS Hydro 35. And if we scroll down a couple pages to the table of contents, there are these ISO Hydro maps for precipitation for the 2-year and 100-year for 60 minutes, 5 minutes, and 15-minute precipitation events. So we'll just go ahead and take a look at this real quick as an example. The 100-year, 60-minute precipitation map is on page 17. So let's just go there. In the PDF file, it happens to be 19, but it says 17 up here in the corner. So I know this is the correct one. Plus, there's a legend right here that says 100-year, 60-minute precipitation. All right, so let's find a location in the eastern or central United States. How about Missouri? We have 3.25. I know the depths here are kind of hard to read, but these are in inches. And then here is 3.5. So 3.5, 3.25. So the middle of Missouri would be right here. We'll call it 3.35 or maybe 3.40. Okay, so back to our toolbox. 100-year, 60-minute has a depth of 3.40. So we would repeat that process. So let's go to the next map. Okay, up a page. Now we're looking at the 2-year, 60-minute precipitation. And then let's focus on middle of Missouri once again. Here's 1.7 line, here's 1.6 line, here's 1.5. So we could say it's between 1.5 and 1.6. How about 1.55? So back to our data input, I'll say this is 1.55. All right. Continuing that process, I already went ahead and checked. I'm going to type in the numbers 0.44, 0.92, and then the 100-year numbers are 0.87 and 1.82. Okay. When I click OK, now what I have is some data in my IDF curve table up here. So what we have is 5-minute, 15-minute, and 60-minute for the 2-year and the 100-year storm events. But then, as you notice, we also have some extra data, some new numbers that have been added in automatically just using interpolation. So there's a 5-year, a 10-year, 25-year, and a 150-year return events that have been added. Those entire rows have been added. And then for our rows for 2-year and 100-year, we have a 10-minute, 15-minute, and 30-minute storm events, which have numbers added as well. I'm sorry, 15-minute we added ourselves, but yeah, the 10-minute and the 30-minute storm durations have been added for the 2-year and the 100-year storm events. Below here is the curve. We can double click, we can modify the properties, we can export if we wanted to save that image. Also wanted to point out this equation right here serves pretty much like a best fit line so that interpolation can be used if the duration of the storm is not exactly 5-minute, 10-minute, 15, 30, or 60 minutes in duration. All right, so that's using Hydro 35 data. If I wanted to click on NOAA Atlas 2 data, Western United States, that's the second option, and then click on Define Storm Data. I was having some problems with this one. It looks like the options are Idaho and Montana for regions 1 or 2, or for Idaho, it was 1, 2, or 3. So I'm not going to talk too much about this, but the next option down is User Supplied Data. So when you make that selection, you can manually define the storm data, or you can get the NOAA Atlas 14 data. I'm going to demonstrate both of these. So let's start with define storm data. So when you click on this, you may get some existing data because we've already entered some Hydro 35 data. What I'm going to do is just real quick create a new rational method calculator. So I got fresh data. Actually, let me go ahead and change this back to 0.55. The area is 40 acres. Okay, so for rainfall intensity, click on compute and then user supplied define storm data. Now we can specify the recurrence year, the storm, 1 year, 2 year, all the way up to 500 year. Let's stick with just the 2 year and the 100 year. And then once we input this data, we'll get computed results up in this table here. I'm going to visit the NWS NOAA Precipitation Frequency Data Server. That's the other link that I have here in my browser. I will leave a link to this webpage in the description of this video. I'm going to click on Colorado, and then I'm going to zoom in by just using the plus button, and then you can pan to sort of recenter on where you want to zoom into. I'm going to be zooming in on Boulder, Colorado. Okay, that's close enough. And then click on the Show Station Map checkbox. All right, let's click on this weather station right here and then scroll down. And we're getting a table of precipitation frequency estimates. These are values in inches. So we're going to have to convert that to inches per hour. But here is the 2-year storm event column right here where it starts with 2. And then over here is the 100-year storm event column that starts with 100. And then each row here represents a storm duration. So we have a 5-minute storm and a 60-minute storm, and then longer storms below that. So what I'm going to do is pluck out the data for 0.251, 0.367, 0.448, 0.628, and 0.782. Now, when I multiply that by 12 and 6 and 4 and 2, I will get my intensity in units of inches per hour. So I've done that in preparation for this video, just for these 5 different storm durations for the 2-year storm event and the 100-year storm event for this particular weather station. If you wanted to check my math or something, I'm just going to type the numbers in here. So 3.012, 2.202, 1.792, and 0.782. Okay, so that's for the 2-year event. And then I'm going to change it for the 100-year storm event and then type in the numbers I have, and 2.44 inches per hour for a 60-minute storm, 100-year recurrence interval. Okay, if I click OK, what you see here is I now have data for the 2-year event and the 100-year event, but there's no data entered for these other storm event durations. Let me make this a little bit wider here. So if I click on one particular storm event, here's the IDF equation, or the 100 years right here. The plot only shows the 2 curves of the data that I input. And I know that that right there is kind of a hassle. So what I'm going to do instead is demonstrate get the NOAA Atlas 14 data by clicking on this button right here. If we know the latitude and longitude, you could type it in. So a positive latitude is northern hemisphere. A positive longitude is eastern hemisphere. So in the United States, we'd have a positive latitude and a negative longitude. If you don't know the exact location, you can click this select latitude longitude from a map. That will bring up a map here, which is already located where I want it to be because I prepared for this lesson, but you can also type in a search term right here. So if I typed in Texas, then it would reposition me to Texas. Oh, hold on, I got to click this button, jump to search location. Okay, there we go. But what I'm interested in is Denver because I wanted to just make sure that my numbers matched. And Boulder is right up here. So let me go ahead and center this. We'll use these lat long that's up in the top left corner. So all I have to do now is click OK button in the bottom right of this interface, and then it updates the lat long. So if I click on OK right here, boom, it automatically searched for all of those numbers. We have 1 year up to 500 year, and then it extends from the 5-minute storm duration up to 24 hours. All right, so we see the plots right here and the equation. Real cool. I'm just going to spot check. How about 5 minutes, 100 year? I have 9.69 when I looked up the data manually. So 100 year, 9.74. That's pretty close. And then one more check. How about the 100 year but 60-minute storm duration? I have 2.44. So 100 year and 60 minutes is exactly 2.44. All right. The next part of this interface is the time of concentration. Now, perhaps you know the time of concentration exactly for the watershed. So if you click on specify time of concentration and you know that it happens to be 30 minutes, then you can compute the intensity right here. It will compute for the selected row. So 100 year, 30 minutes, it should return right here, 4.03 or something close to that. So click compute intensity, 3.886. Okay, that's a little bit off. And the reason for it being a little not exactly 4.02 is because it's using this best fit curve. Let's go ahead and just say it's 5 minutes instead. So it should come out with something close to 9.74. So 5 minutes and compute 9.74 exactly. Now we can't interpolate between storm events, but we can between storm durations. So let's go ahead and just pick on the 10-year storm, and then we'll say it is 22 minutes, which is about halfway between 15 minutes and 30 minutes. So the intensity here in inches per hour should be about between 3.08 and 2.51. So it should be close to about 2.4, 2.5. So let's set that to 22 minutes. Click on compute intensity, 2.497 inches per hour. So that's how to calculate the intensity if you have a specified time of concentration. If you don't know the exact time of concentration, you can use the compute TC tool. So click on this radio button and then click on define parameters. This brings you up to a calculator tool, which includes 3 different parts for your time of concentration. There's sheet flow, shallow concentrated flow, and channel flow. If you don't want to use any of these 3 parts, then you can just uncheck that checkbox to disable it. But let's just go ahead and type in some numbers to make sure that this works. Also, the user's manual, if you scroll down a little further, it describes this time of concentration calculator, which I'm going to use for these exact numbers. And it goes through each step. So the first part, it talks about the overland sheet flow. It has some numbers right here, and it has an equation. Below that, it has the shallow concentrated flow with some numbers and a different equation. And then finally, it has the channel flow, which you're probably more familiar with, Manning's equation, and then some more example numbers right here. The channel flow would be for an existing channel or storm drain system. And then backing up, the shallow concentrated flow, this would be, for instance, flow that's in some sort of collector, a small collector like a gutter. And then finally, the sheet flow or overland flow, this would be like flow along a roadway or a parking lot, but not concentrated in any sense of the word. All right, so I'm going to go ahead and type in the numbers that they used, 2595. Halfway through entering the data, there's this K value here that ranges from 0.076 to 0.619. And it says to see the HDS2 table 2. But that table is also available in the user's manual where we see values of K versus different land cover. So if you need an idea of what to put, basically the more impervious the land cover, the higher that K value. All right, so just wanted to mention that. All right, so I'm in this last part here Finally, we need to define the channel as either a curb and gutter calculation or a channel calculation. So if you already have an existing channel that's defined in your project, you can use that, or a curb and gutter calculation, you could use that as well. You can also create a new channel by clicking on create new, or just use an existing channel analysis. So I'm going to use existing. And then it looks like after entering all that data, the time of concentration calculates out to 10.5, and that's in minutes. If you do use an existing channel calculation or a channel analysis, then you need to make sure that your elevations match up. Oops, hold on, 2591. There we go. And if not, it'll give you an error warning, and then you'd have to go back and modify your elevation values. Okay, so 10.563. Oh, here's the warning right here because my channel was a little bit goofed up. The elevations didn't quite match, and that's not surprising because I'm using just someone else's example numbers. So I'm just going to use this, click this button to set calculator slope to match calculated slope, and then be done with that. It came out to a time of concentration of 10.6 minutes right here based on those calculations. So computing the intensity came out to 3.725 inches per hour. That's based on the 10-year event. So if I changed it to a 50-year event, then it increases to 5.904. All right, sometimes this calculates automatically. Sometimes I find myself clicking on this compute intensity button. So it may be safe to just click on compute intensity. And then that rainfall intensity of 5.904 should be copied over into my main rational method calculator right here when I click OK, or how about done? Okay, there it is, 5.904. And then the time of concentration, 10.56, recurrence of 50-year, and 131 CFS is the calculated peak discharge for the numbers that I'm using here. It's not mentioned anywhere in the user's manual, but there is a button here to compute hydrograph. So if you click compute hydrograph, you've got a few different options. Now, this isn't really part of the rational method, but it shows up in the display anyway. So sort of use this feature at your own discretion. But if you click on one of the hydrograph methods, click OK, and then boom, it gives you a time in minutes versus the flow rate in CFS. It looks like the peak flow rate is, what was it, 126 at 50 minutes. Okay, so I got 131 right here. Well, anyway, that's it for this lesson. What we did was use the rational method calculator in the FHWA hydraulic toolbox to calculate the peak discharge or the peak flow rate from a watershed using this calculator.